All right, so welcome back. In this video, we're going to look at the beginning of the next section, which is at first on the notion of a union. So the notion of a union is, well, probably something you're already familiar with to some extent, right? So we have our Venn diagram, and we have two sets, A, B, and the region here, which intersects A and B, is what we're going to call the set A union B. So that is the symbol that we are going to use for those of you who use LaTeX, cup. This is the name, that's the name of that symbol, cup. So A cup B means A union B. Normally it's read A union B. And A union B is not a sentence, right? It's just the name of a set, but it's the name of a set that contains all the objects that are in A plus all the objects that are in B. Now, typically in set theory, we're not happy with just taking the union of two sets. We want to think about the concept of taking the union of an arbitrary number of sets. So maybe we'll have all of those here. I don't know. They don't have to all overlap. Then we're going to want to take the union of all those sets. So that would include all of this area here. Right? And that would be the union of those sets. Now, how are we going to denote that? Well, what we're going to want to do is form something that we'll call a collection of sets. So we're going to use that fancy scripted letters to talk about a specific kind of sets, namely collections of sets. Now we know we can form collections of sets because we have the pairing axioms that tells us take two sets, form a new set with those two sets. That's a collection of sets. Right? So suppose I give a name to those sets here, A, B, C, D, E, F. I could say that the collection of sets in question here contains A, B, C, D, E, F. All right, so in order to have a good notation to talk about the union of an arbitrary number of sets, what we're going to do is we're going to take the union of that collection, which means this, union this, union this, union this, union this, union this. But it could go on infinitely, right? And we don't want to write dot, dot, dot. That's not rigorous enough for the foundations of mathematics. So we're going to have this new notation where we're going to be writing with a big cup this time, the union of a collection of a collection of sets. Again, for those of you who use LaTeX, that's big cup or union of a collection. But now at this point, we don't know yet that we can form arbitrary unions like that. No axiom tells us that it's valid. And so we need to introduce a new axiom that is going to enable us to do that. And this is called the union set axiom. And it says the following. For any collection of sets C, there is a set U. I'm using the letter U just so we keep in mind it's about union, right? There is a set U such that for all x, x is in U if and only if the following happens. If and only if x is in at least one of the members of that collection. And that's how we write it. If and only if there exists a set such that X is in the set, and furthermore, the set is in the collection. Okay? So for any object, X is in that big set here. If and only if, well, the collection contains S and S contains X. So you could think of here X being, let's say, if X is in B, then it follows that X is in at least one of those 6 sets which constitute the collection. All right? And that's going to mean that X, as a result, would be in that set U right here. Now, that set U is going to be our union set. In fact, in the notes, now that I'm looking at that, in the notes I wrote it as a conditional. In fact, I wrote it as a conditional going in the other direction. I said, yeah, if X is in one of those sets in the collection, then X is in U. The reason it's written like that is just because it's I don't know, it's just an exercise in style. That's the standard way axioms are written in set theory, where U could be a set that contains a lot more than just those objects that are in the sets in the collection. It could contain all sorts of other junk. And for some reason, that's how the axioms function. And then immediately after introducing this axiom, what we do is we use the axiom of separation to say, hey, now we want a set that contains exactly those members of the sets in the collection. So that's what we're going to do now. We're going to introduce a definition. And that's going to be the definition of the union of a collection. So the union of a collection, by definition, is the set of things that are in that set U here. But we want to make sure that it contains only those that come from the sets in the collection. And we're going to use the axiom of separation to do exactly that. So this way, an element is in the union set if and only if it happens to be in one of the sets in the collections. And that gives rise to a couple Fitch-style rules that we can use to talk competently about union sets. So we can say X is in the union of C, and we can derive from that that there exists an S such that X is in S, and furthermore, S is in the collection. X is in the union set, just in case it's in one of the sets in the collection. And we can flip things around and to say, well, if we know that X is in some set in that collection, then it follows that X is in the union set. By the way, just in case you think that this looks overly complicated, that formula here is just a sentence like in Aristotelian logic, right? That really is just there exists an S such that X is in S and S is in C, right? It's the lower left corner of the square of oppositions. That might help to keep those things in mind. All right, so let's look at how we would prove some of the properties of that union set operator. First I want to mention just one more thing, right? I want to mention that though I've just introduced the following notation for the union of a collection, There are two other notations that are fairly common in textbooks and articles. So the first is the following. All right. So, I mean, one thing that is fairly clear is that for any set A, if we consider the set of objects that are in A, well, that's just the same thing as the set A, right? So this is why those two notations are exactly similar or equivalent. Sorry. And another one that is used quite frequently is to take the union ranging over all the sets in C. Right? So the union of all the x's such that x is in C. That's yet another way of writing the union set. The three notations are fairly common. I'm going to use that one fairly often, and that one occasionally as well, because it's sometimes useful. Okay, so let's start with something fairly simple. Theorem. For any set A, if, oh sorry, what was it? Yeah, if A is in the collection of sets, then A is a subset of the union of the collection. Yeah, what is this? That's very easy. Right, so our collection of sets is going to contain, I mean, we don't know how many, but that's just an example, right? So the collection of sets is going to contain A plus some other sets, perhaps. Now, since the union of the collection contains all the objects of each of the sets in the collection, it's of course going to contain all of the elements of A. That is to say, A is going to be a subset of the union of the collection. So I hope intuitively that makes sense that this should be true. But we're going to try to write it a bit more like in our Fitch diagram, right? So our first line in the Fitch diagram would be that A is in the collection. And our last line would be that A is a subset of the union of the collection. Now, our sub-goal is to show that something is a subset of another thing. So normally we proceed by a conditional proof where we assume that some arbitrary object A is in the left-hand side, and we try to show that as a result, it's in the right-hand side. So if A is in capital A, then A is in the union set of C. Now, in order to reach that sub-goal, we're going to want to use the membership condition for unions. Right, I forgot to mention that before. Probably I should have. Right, so if X is in the union set of a collection, then that means there exists a set such that X is in the set and the set is in the collection. X is in the union set if X is in at least one of the sets in the collection. And that works both ways. We can flip things around, and all of those would be membership of unions. And that's what we're going to be using here. So there exists an S such that A is in S and S is in the collection. That's what we want to get. Okay. Now here we have an existential quantifier, right? So we might want to reach that by showing an instance, right? And then doing an existential introduction. But of course, we do have exactly that. We know that A is in A. And furthermore, we know that A is in the collection. So that was our premise. That was a supposition for conditional proof. That's just conjunction introduction. And then on line 4, we do our existential introduction from line 3. And on line 5, it's just the membership condition for union sets. And on 6, it's just what? CP plus for all int from line 2 to 5, something like that. All right, so then it's going to be easy to write that in words and have a very clean, beautiful proof written in English, just like they would ask you to do in a class in math or linguistics or microeconomics or computer science or whatever. So here's another one that is interesting. The union of the empty set. What? What is this? Right? So here we have a collection. Right? That's our collection. But now the collection is the empty set. So that's the one that contains nothing. Right? So now let's look at our membership condition. There exists an S such that X is in S, and S is in the collection of sets, but now that's the empty set, right? So now we see that nothing is in the empty set, so the second conjunct is always going to be false, which means the conjunction is always going to be false, which means that this entire sentence is always going to be false, right? So we can see that for all x, x is not going to be in the union of the empty sets. Another way of saying that is to just say, well, the union set of the empty collection is itself the empty set. The more rigorous proof is given in the notes. I just wanted to give you the idea. Now, what about the union of a specific collection, namely the collection that contains only the set A? Right? What would that be? Well, we have a collection that contains only A, right? So again, let's write our membership condition. There exists an S such that X is in S and S is in singleton A. Now, this only happens in one case. That happens if S equals A, as you remember from looking at the singletons in the last video, right? And so the first part means this, right? That's going to be true just if we have X in A. So the only objects X for which that sentence is going to be true, that's going to be for those that are in A. So the union of a collection of set, where the collection is just singleton A, is itself the set A. And now we get to an interesting case. Well, another interesting case. Of course, they're all interesting. We're going to take the union of a collection that contains two sets. And that's going to be, well, guess what that's going to be? That's going to be exactly our case where we want X to be in that union set if it's either in this one or in this one. It has to be in at least one of them, right? So the union of that pair of sets, that is going to be our official definition for the thing that you've been used to seeing all this time, namely the binary union. The union connecting two sets together is, guess what? It's our general union operator that we introduced with the union axiom, but applied to pairs of sets. All right? And that is going to be our axiomatic justification for talking about binary unions. Fairly easy, I hope. As a result of that, well, we're going to have two membership conditions for the binary unions, but two rules involving them. So, whoa, what am I doing? Suppose we have X is in A union B. That's going to tell us that X is in A or X is in B. So in terms of our big definition for the union set, we had the following. But now the collection contains only two sets, namely A and B. So for X to be in some set which is in the collection, that means X has to be either in A or in B. And we can flip things around. If X is in A or X is in B, it follows that X is in A union B. Okay? So now that we have the definition for our union set, we can write explicitly some of the properties of this union set. So that's a theorem. I don't remember which number in the notes, but that's a list of five properties of unions. So the first property has to do with the union of A and the empty set. What do you think that is? So that's the set that contains all the elements in A plus all the elements in the empty set. Now there are no elements in the empty set. So that's going to be just the elements of A. So A union empty set equals empty sets. Equals A, sorry. And that's called the null element property. Why is it called null element? Because it's a bit of an analogy to A plus 0 equals A, right? 0 is the null element here. The second property is A union B equals B union A. So that's commutativity. Commutativity of union. If you try to do the proof, and you may have to do it, that's going to be based on the idea that this junction is commutative, because something is in that set, say X is in that set, if it's in A or it's in B. But that's the same as saying it's in B or it's in A, which gives you the membership condition for that. So that's straightforward. The third one says that A union B union C with the parentheses around the last two is the same as A union B, close parenthesis, union C. That's what we called associativity before. So binary union is associative, and as a result, you can omit, after you've proved that, you can start omitting parentheses because we know that it doesn't matter where we put them. All right, suppose I take the union of the set A and the set A. The result is a set that contains all the members of A plus all the members of A, which of course is just the members of A. That's the idempotence property. And the last one is a little bit cool. So, by the way, those I'm not proving because they're fairly straightforward, so probably they'll be in your exercise and things like that. This one we're going to actually try to prove. So it says something about the relation between subsets and unions. So if A is a subset of B, but not if and only if A is a subset of B, A union B equals B. Why? Because think of it, right? If A is a subset of B, here I look at all the objects in A plus all the objects in B. Well, that's just going to be the objects in B, which is why it's going to be equal to that set. So let's just look at how the proof would be constructed for that. Well, there's going to be two parts, right? There's going to be a part that goes from A is a subset of B and ending with A union B equals B. And then there's going to be a second part with A union B equals B and ending with A is a subset of B. What are we going to do? Well, let's start with the right-hand side, just because it's going to be a little bit easier, I think. So we know it's a conditional proof, where we take an arbitrary object and we suppose it's in A, and we want to end with saying that this arbitrary object is going to be in B as well. Okay? Now, from the fact that A is in the set A, it follows that either it's in A or it's in B. Now that's disjunction introduction. That's simple, right? It follows that it's in A union B by the membership condition of unions. But then since A union B is equal to B, it follows that it's in B by extensionality. And that's what we wanted, so we're done. That was easy. For the second one, I'm going to leave a little bit more room because we might need it. Let's subset. All right. So we look at our thing. Our conclusion says that this is equal to this. So our first reaction should be to think, hey, I'm going to use the anti-symmetry of subsets in order to get there. So I'm first going to show that A union B is a subset of B. And then I'm going to show that B is a subset of A union B. Two parts. So let's start with the second part, just because, again, it's easier. So that's not going to be a big deal. So suppose some arbitrary object is in B, right? It follows that either it's in A or it's in B. That's just, again, disjunction introduction. And so it follows that it is in A union B. And that's exactly what we wanted to have. So the reasoning, out of the scope. The reasoning is fairly straightforward here. So let's look at the second one. I'm just going to erase that again to have a little bit more room. Not that it's huge, but just to make sure it's that I'm not writing too small and that you can read on the screen. Okay. So we're going to start with A is the subset of A union B. And we want to get with A is in B. Now our membership condition tells us that either A is in A or it's in B. And when you see unions like that, it's going to be very important to understand that unions are disjunctions in disguise. And when we have a premise or something at the top of our Fitch diagram, which is a disjunction, it tells us, it yells super loud, please, please, please do a proof by case, a disjunction elimination. Yes, so we're going to do it. So first case, A is in A. And second case, A is in B. Well, guess what? And what we want to get is that A is in B. Now, of course, that's easy. That's just reiteration. Now, if A is in A, well, we know that A is also in B because of line 1. But that's it. That's all there is to it. We don't even need to write that. Okay? So there's a more carefully prose written proof in the notes, but I thought not to just duplicate what's in the note. I would do it as a Fitch diagram here. All right? So this is how you go about making those proofs using the binary unions. Okay. So now let's start looking at something else. Well, the natural continuation of our topic. Now that we've talked about unions and clarified all of that, we're now going to be talking about intersections. Now, when we started talking about unions, we needed to have an axiom that allowed us to talk about unions. Why? Because we need an axiom that tells us that a set exists. We're not allowed to just assume it out of nowhere, right? We really need to be absolutely sure that it's authorized by an axiom. And unions are about making bigger sets, so we cannot assume already that they exist. The axiom needs to tell us that. But intersection takes already existing sets and makes smaller sets. So this is why we don't need to introduce an axiom of intersection. We can just get away with introducing it by definition using the axiom of separation. So just to give you the easy case with binary union of what I'm trying to explain here. All right, so suppose I take two sets, and I have A, B here. And the union axiom tells me that there is a set that contains exactly the objects in the green part. Now notice that the objects in the red part are among the objects in the green part, right? So I can just take the set corresponding to the objects in the green part and separate it in two, namely those that fall here and those that don't. So this is going to be exactly the idea. So my board is getting increasingly dirty. If you just give me a second, I will wash it a little so you can read. And we're going to hope that everything is clear and simple. Not as good as I want, but now you see how much time I'm spending between each video cleaning the board. Well, it's that plus a lot more. Okay, so we're going to want to use separation. We're going to want to talk about the objects that are in the binary union. I could have written A union B here if I wanted, but I'm writing that just to keep reminding you that this is known to exist by virtue of the union axiom. But now we want to restrict ourselves to those things that are in A and in B as well. And this is what we're going to write as A intersection B. Now that symbol is known as cap. So A cap B, but normally it's read A intersection B. Now, in terms of Fitch style rules, that's going to be, again, fairly easy. Suppose A is in the intersection of A and B. It follows that it's in A and that it's in B as well. Okay. We can flip things around. Suppose X is in A and X is in B. It follows that X is in A intersection B. So that's just like you would expect, right? Given the membership condition. What is the name for those rules? Membership condition for intersection. Both of them. So now that we have a serious, honest, rigorous definition of what intersection is, we are ready to start looking at some of the properties of that operator. So, again, that's based on a theorem. I don't remember the number, but the first part of 6 parts says A intersection empty set. And what is this? Well, it's all the things that are both in A and in the empty set, but there's nothing in the empty set. So there's nothing that is both in A and the empty set. Empty set. Again, that's the null element property. Just like in algebra, we have A times 0 equals 0. You see the connection there, right? In fact, in general, in mathematics, there are amazing connections that we should keep in mind. We already saw that there was a close connection between the disjunction and the existential quantifier, right? Which is not an accident that for unions, we have a connection here as well, because the membership condition for unions started with an existential quantifier. And so if something is in the union, that means either is in the first set of the collection, or it's in the second set of the collection, or it's in the third set of the collection, etc. But also, I mentioned that there was a connection with plus in terms of the property of the null element, and we could have looked at the other ones too. We also earlier looked at the connection between conjunction and universal quantifiers. And now we see that there's also a connection with the intersection and multiplication. It's a fascinating topic to see how deep those connections go. And you'd be surprised to see that they share many of the same properties. But that's just an aside, right? Just a little side observation that I wanted you to make, because, I don't know, it's fun to think about just how deep it goes. So now you have a project for the week. All right. Guess what? Intersection is also commutative. Doesn't matter, A intersection B, B intersection A, same thing, because conjunction is commutative. Guess what? Conjunction is also associative. All right. What's the next one? It's the idempotence. So A intersection A just is A. I hope that makes sense. And now we have one that is a little bit like property number 5 for union. That one says that if A is a subset of B, then the set A intersection B equals, what do you think it's equal to? So all the members of A are members of B. So the objects that are both in A and in B Well, that must be just the objects that are in A. It has to. And finally, there's a sixth one here, which is quite useful. It says that, what does it say? It says that if A is a subset of B intersection C, if we have that, then it follows that A is a subset of B and A is a subset of C. Again, I hope that makes sense, because if all the objects that are in A are both in B and in C, then it follows that all the objects that are in A are in B, and furthermore, that all the objects in A are in C. All right. There are some of the proofs in the notes. I'm not going to go through all of them because it's very similar to what we've done for the disjunction. We just replaced the disjunction by conjunction, basically. There are a couple of properties that I'll mention about the connection between binary union and binary intersection. And this is the following. You remember the distributive laws that we had in logic for disjunction, distribution laws for disjunction and conjunction? Well, guess what? We have the same. A union B intersections, whoops, not B again. A union B intersection C will equal what, do you think? A union B intersection A union B intersection A union C, maybe? Don't know. I'm starting to feel that I have a little bit of fever, so maybe I'm getting it wrong. Let's just check by doing a Venn diagram, right? So we have A, B, C. Right, so B intersection C is that part. And if we take that union A, then we get all of that, right? So here we have the left-hand side. So let's do the picture a second time. This time for the right-hand side, and we'll see if we get the same picture as an end result. So A, B, C. So A union B is all of that up here, right? And A union C is all of that stuff here. So if we take the intersection of the two, we get what? We get this here, which is not the same. That means I got my distributive law wrong. Oh, what did I do? That's a crime against logic and set theory. La la la. What are we going to do? I don't know. That board is dirty. What are we going to do? We have to rectify the situation. Ah, what a disgusting board. What are we going to do with that? Well, I'm going to try to survive somehow. Maybe I just got the order wrong. That's possible. A intersection B union A. That would be A intersection B. Oh, yes. Union A intersection C. I think that's going to be right. All right, so A, B, C. We have B union C, and A intersection is here, right? And that's A intersection B union A intersection C. Good, that works. So that's yet another property here. Again, I'm not going to prove it, because I just want to tell you about the intersection, which is the general concept of intersection, not just the intersection that applies to pairs of objects. So what do I mean by that? Well, just like we had the binary union as a particular case of the union of arbitrary set, we also want to make the intersection of arbitrary collections of sets. So we're going to try to have something like that with that big cap operator, just like we had for the unions. Now we're going to have, we want to introduce a definition. But the first thing I'm going to do here is to say first, for any non-empty collection of sets C, the definition is going to apply. But the definition is not meant to apply to empty collections of sets. Now, just like the binary intersection is a subset of the binary union, the arbitrary intersection is going to be a subset of the arbitrary union. So the set we're going to separate in two is going to be the union set of the collection. But it's going to be the one such that X belongs to every set in the collection. So for all S, if S is a set in the collection, then X belongs to S. So again, you see that connection between the universal quantifier and the conjunction, the one that we have noticed before. So for the Fitch-style rules, we would have, well, X is in the collection of sets. X is in the intersection of the collection of sets. That means that for all S, if S is in the collection, then X is in S. X is in every set in the collection. That's what it means. And the other way around is not quite just flipping things around, but almost. So if S is in the collection, then X is in S. But we also want to specify that the collection of set is not empty. And if we have both of those things, then we can say that X is in the intersection of the collection. We have this second part just because the definition doesn't apply to empty collections. So both of those rules are just membership condition for the intersection. Now, you might be wondering, why did we say that the definition applies only to non-empty collections? We didn't do that for unions, right? We could talk about the union of an empty collections, and that was just the union set, the empty set, as we saw earlier. Well, let's inspect our membership condition a little bit, right? So for all S, S is in C, arrow, X is in S. Now, in the case that we consider where the connection, well, the case we want to exclude, really, but we're trying to understand why we want to exclude it. We're looking at the case where the collection is the empty set. It's an empty collection. Well, So nothing is in an empty set, right? So that means the antecedent would be false for any set. That means the conditional would be true for any set. So since for all x, for all x, the membership condition is true, right? So that whole thing is true always for any object x, because again, the antecedent is false. That means that for all x, x is in the intersection. Well, or not in the intersection, but in what would be defined if we allowed C to be empty. Now that means that this is the set of all sets. It contains everything. So among other things, it contains the set of all sets. But now, as we saw, we introduced the axiom of separation specifically to not be able to prove that there exists a set of all sets, because if it did, then we could do Russell's argument and obtain a contradiction showing us that set theory is an inconsistent theory. And if it's an inconsistent theory, it's certainly not a good way to provide foundations for mathematics. Okay? So the idea of restricting that definition to non-empty sets is precisely that, well, if we didn't require that, we would obtain contradictions, and that would ruin everything. Everything. And we certainly do not want that. Now, just as we had two alternative notations for unions, we also can write the intersection of the set of x such that x is in the collection. That's also fairly common. And so is the following notation, which is also fairly common. Okay, so now let's look at an interesting case. Well, it's fairly simple. It's not super interesting, but it is interesting nonetheless. Okay, so we're going to have the following theorem. I'm not going to use the quantifier here. I'm going to write it in words. For any collection C, if the empty set is in the collection, then the intersection of the collection is itself the empty set. All right, so we're not allowed to take the intersection of a collection of sets that contains no sets. It's not really much of a collection of sets. But we're allowed to take the intersection of a collection of sets that contains the empty set and perhaps other things. And the idea is that, well, if we take all the elements that are in here and in here and in here, well, there's none here. So we're not going to have objects that are in here, in here, and in here. That's why we get that it is in the empty set. Okay. So how would we go about showing that? Well, we would start with the assumption that the empty set is in the collection. And we try to get to the conclusion that the intersection is the empty set. Now, the beauty of that is that we had a theorem that told us that the empty set is a subset of any set, right? So that is just from a previous theorem. I think it might have been the first theorem that I did in those video lectures. So that one, we don't need to prove it again. We can just appeal to what was done before. So now all we need to do is to show that the that the intersection of S is a subset of the empty set. So that means we're going to take an arbitrary object, assume it's in the intersection, and then take an object and show that it's in the empty set. A. Now you might be thinking, well, how are we going to get A is a member of the empty set? That's the empty set. It contains nothing, right? Well, if we manage to derive something which is false, that must mean this is already false. That must already involve some contradiction. So what we're going to do is we're going to suppose that A is not in the empty set, and we should be able to get a contradiction because, as I suggested, this should already contain a contradiction. Now, by the membership conditions, that tells us for all S, if S is in the empty set, then what? Then A is in S. Right? So that should be okay. Now, what are we going to do? What are we going to do? Oh, yes, we're going to do a modus ponens, perhaps, right? So, wait, this is in the collection. So S is in the collection. The empty set is in the collection. Wait, what am I doing here? I'm so sorry. That's why I'm getting it. Right, the membership condition here gives me C, obviously. Good. So now I could instantiate that sentence to get if the empty set is in the collection, then it follows that A is in S. So that shows that, oh, sorry, I forgot something. Right? I have to replace S, both occurrences of S by the empty set. Now I know that the empty set is in the collection, so I do a modus ponens. A is in the empty set. But as we saw, nothing is in the empty set. Why? Because by virtue of the membership condition of the empty set, that implies that A is not A, and also A is A. So that's a contradiction, and that leads us to the conclusion. All right, so that's it for this video. I hope it makes sense and that you can watch it on your own time while looking at the notes alongside, and that it's working quite well. So I'll have another video coming soon about the rest of that chapter, and I hope that you're going to find it interesting as well. All right, cheers.